Hello everyone. Welcome to our today's presentation on switching over voltages. My name is Arash and I'll be your presenter today. The switching study is necessary to determine the overvoltage levels due to switching events, such as energizing or de-energizing a line, to determine equipment insulation levels, assessing surge arresters' capabilities, and identifying network resonance issues. Switching over voltages occur during operation of breakers or switches. The switching action creates traveling waves on the transmission line, which causes the oscillation of the circuit LC elements. These oscillations can appear as a high-frequency voltage transient in the network. The switching transient frequencies can reach up to a few kilohertz. International standards such as IEC define a frequency spectrum to categorize different transients. As we can see in this table, the switching transients are categorized as the slow front transients. That would be the main focus of our today's presentation. In order to perform a switching study, the area of interest must be modeled correctly to capture correct switching over voltages. Now, what do we need to include in our model? Well, the system must be represented at least up to 2 buses away from the point of study. It is recommended to use a frequency-dependent transmission line model. We'll talk about this in the next few slides. Detailed transformer model including saturation data, shunt devices, surge arresters, nonlinear VI characteristics, and equivalent voltage source models to represent network boundaries and generators. As shown in this example case, the network has been modeled up to at least 2 buses away from the area of interest. So the area of interest for this case is a tie line between the north area and the south part. Some of the buses have a generation unit connected which has been modeled as an equivalent source, or even boundary buses are defined with an equivalent source. Also, smart part of the low voltage side was also modeled, a 230 kV level and also a 132 kV level. For a network boundary equivalent model, we need to define the voltage bus and angle, a real power and reactive power generated for that bus, the positive sequence impedance, and a zero sequence impedance. There are 3 types of transmission line model available in PSCAD: pi section model, Bergeron model, and frequency dependent model. Pi section model is only valid for fundamental frequency, 50 Hz or 60 Hz. It does not represent the traveling wave characteristic of transmission lines. The line is only represented as an RLC circuit. Therefore, it's only suitable for load flow type studies. Bergeron model, however, represents the traveling wave characteristic of the transmission line, and it's only accurate for the specified frequency. On the other hand, the frequency-dependent model is valid for all frequency ranges, from a DC to megahertz, and also represent the traveling wave characteristics of transmission line. Therefore, this will be the most suitable model to use when we're doing the switching studies. For the transmission line cross-section, we need to make sure we model the actual tower, the location of conductors, the way they are arranged, ground clearance, line sag. Remember, if you are modeling the tower for the line you're studying for switching study, you have to make sure you're using the tower geometry correctly. As shown here, the conductor data and ground wire data also needs to be entered correctly. Values like a conductor type, radius, DC resistance, the bundle data, sag. Now, if the study line is a long transposed line, to model it, we need to divide the line in multiple segments and connect them as shown here. So on the top, we have a 200-kilometer line, which is untransposed. So if you need to model it without any transpose, you can just use the transmission line model with the correct length. But if you need to represent this 200-kilometer line in a 4 segments or transpose 4 times, you need to divide the line into 4 segments, each 50 kilometer, and transpose them externally, as shown here in this example. Transformer model. You can use the general data, like a rating impedance, and also you need the saturation data for the transformer. These data can be obtained from manufactured data sheets. Shunt devices. If there is any shunt devices close by the line we are studying, or if there's any line reactors, you need to model them as with equivalent inductance or capacitance. And you can calculate the value of L and C's according to this formula by knowing the kV level of the bus and also MVR of the reactor or capacitors. You can calculate L and C values. Generators, similar to equivalent network model, you need to identify the bus voltage and angle, real and reactive power generated by the generator at that bus, and the positive sequence impedance of the generator, which is the X double prime D. The zero sequence impedance, if it's available, you can enter. Otherwise, you can leave it as a default. For surge arrestor model, you need to know the arrestor rating, the VI characteristic, and also the energy absorption capability to generate the VI parameters of the surge arrestors. Sometimes the data sheet provided by manufacturer is not sufficient to create a full VI curve. As shown here in this example, in the graph, the blue line represents the curve based on data provided by manufacturer. However, to generate the lower portion of the surge arrestor VI characteristics, we need to tune those data such that we get a lower portion of the surge arrestor VI characteristics. Remember this, the lower section needs to be tuned such that the current is very small. If the manufacturer provides the complete test results of the surge arrestor VI curve, then you need to use the data provided by the manufacturer to get an accurate result. For a cable model, similar to transmission line model, it is recommended to use a frequency-dependent model based on the cable design data. Also, in latest version of PSCAD, there are some additional new cable models available. They will allow user for more realistic representation of cables. For example, a pipe cable model or a 3-cable flat configuration or 3-cable in trefoil configuration. Once the modeling is completed, the next step is to validate the model before performing the study. You can validate the model for load flow and fault level. The load flow and fault level can be generated from the other load flow programs such as PSCAD or from the actual field measurements. In next few slides, we'll show some of the examples of model validation. In this example, the load flow and fault level compared with other load flow programs such as PSCAD. As we can see in the tables for the power flow and fault level, they're pretty close. And they are within the acceptable range. Here in this example, we are comparing the PSCAD results with the field measurements. And we'll see they're in a good standing. Once the model is validated, you can set up the simulation for the switching study. The switching overvoltage magnitude is primarily dependent upon the statistical variation in the point on the voltage waveform at the instant when the current arc is established between the various breaker poles. In order to capture the point-on-wave impact, each simulation scenario can be run 100 times or more if needed over multiple simulation runs. The breaker closing sequence is then determined by randomly generated pole closing times using the statistical breaker model available in PSCAD. The breaker opening and closing time should be selected such that the maximum trap charge is achieved. This will demonstrate the worst-case switching overvoltage. You can also set up various scenarios to capture network worst case, for example, N-1 or N-2. As mentioned before, in order to capture the point-on-wave impact, each simulation scenario can be run 100 times over multiple simulation runs. At each run, the nominal breaker closing time is advanced by 1/100th of the power frequency cycle. So as shown in this example, each of these points, T1, T2, up to Tx, are 1/100th of a 60 Hertz signal. That means the breaker will close at time T1, the next run it will close at T2, and so on and so forth, and capture the maximum overvoltage for each switching at each of those instants. PSCAD multiple run component can be used to automate the point-on-wave analysis. The components are shown here. If the number of recording signals are more than what is allowed in the first component, you can use the second component to record more signals. As mentioned earlier, the breaker closing sequence is then determined by a randomly generated pole closing time using the statistical breaker model available in PSCAD. The statistical parameter used to represent the pole pre-strike phenomena, and they can be set up accordingly within the configuration file. So the mean value here is the mean value of the minimum time delay and the maximum time delay. For this example, the mean value for two standard deviation is about 12 milliseconds. Then 3 signals selected randomly for each pole. If the line we are studying does not have any line reactor or a shunt device connected to the line, when we open the breaker, as shown in the first figure, we can see the trap charge in the line. The closing time should happen soon after opening to generate the maximum possible overvoltage. However, if there is a line reactor in service, there will be an oscillation between the line reactor and the LC elements of the transmission line. Therefore, you need to consider the dominant natural frequency of the line reactor and the transmission line L and Cs when closing the breaker to capture the worst case switching over voltage, as we see in this example. So the dominant frequency is much slower than the system frequency. So when we're closing the breaker, we need to make sure we close it in the right time that generates the maximum possible overvoltage. In this slide, we see an example of setting up various scenarios for switching studies. So if the line is a double circuit line between station X and Y with the line reactors connected, we have multiple scenarios. For example, we can have a reactors in service, out of service, circuit B out of service, circuit B in service, switching from station X, station Y open, or vice versa. Also, you can consider the scenarios when the lines coming into the stations, the other lines coming to the stations, are in service or out of service to capture the worst case possible. This is an example of a graphical representation of the results. So we'll see the voltages at the switching end and open end, and when the line is out of service. So we'll see the induced voltage on the out of service line is pretty much less than 0.1 per unit. And we can see the energy of the surge arrestor. Obviously, the surge arrestor open end shows the highest energy compared to the switching end. Here is a sample of the statistical results of a switching study. So we'll see the mean value for the open end is about 656 kilovolt, while the switching end is about 470. You can compare these values with switching installation level of the equipment to make sure there is no violation. Similarly, the energies provided here, they are in kilojoules, so you need to make sure those energy does not exceed surge arrestor capability. Thank you for listening to our presentation. There will be a question and answer period after I do a PSCAD demo. We read the questions and try to address them all. However, if we couldn't address your question, please send your question to our PSCAD support. So in this demo, let's focus on the line we're doing the study first before I show you the rest of the system. This is a 200-kilometer line, a double circuit line connecting bus 4 to bus 5. If I go inside the transmission line, you'll see we have a detailed tower geometry and the location of conductors and the bundle configuration. We are using a frequency-dependent model, and this is a 200-kilometer line. At the end of each circuit, there is a surge arrestor installed, and there are switches connecting the line to the main bus. To generate different scenarios, we can use these control signals here to create different setup for the line. Now, if I zoom out, we can see the whole circuit. The boundary buses are represented with equivalent source. We try to model 2 buses away from this study line. And all the shunt devices are represented in the model. We are interested in some measurements, and the point we are interested in are the voltages at the end of each line, and also the energy of each surge arresters. As you can see here, these are the parameters we are monitoring. Also, we are recording the maximum voltage during each run. Now, if I show you the multiple run, if I double click, the output of multiple run is the closing time of the breaker. As you can see here, we are changing the opening time from 0.5 to 0.5167 seconds, which is a 1 cycle of a 60 Hertz system. In each run, we are incrementing the previous value by 1/100th of the fundamental frequency. Before you run your switching study, because we are looking at kilohertz phenomena, we don't need to run the simulation for a long time. 1 or 2 seconds should be sufficient enough to capture the switching over voltages. If I activate the multiple run, and I press run, as you see at the bottom, the case starts running successfully. And now starts the second run. It will run 100 times. So I'm going to let this case to run, but I ran the case before and I can show you the results to save some time. So this is the voltage for the worst case scenario. So we see we have a trap charge, and it appears the maximum overvoltage at the opening end is close to 2.2 per unit. The line out of service does not show much voltage induced on it, as expected. And when we look at the energy, because the out of service line doesn't have much voltage, the energy dissipation by the surge arrestor is almost zero. But we see here, because the overvoltage is high at the open end, we see the higher energy. So the energy is about 490 kilojoules. One way to see if this energy exceeds the capability of the surge arrestor is to calculate the kilojoule per kilovolt of energy and compare with the data sheet. For example, in this case, the surge arrestor MCOV is 360 kV and the energy is 490. That means the kilojoule per MCOV is about 1.4 kilojoule per MCOV. You can compare this value with the manufacturer recommended data. And if you look, if you remember from the presentation, if I quickly go back, the absorption capability was 13 kilojoule per kV MCOV. So that means for the worst case, it will be 1.4, which is well below the rated value of the manufacturer. So we should be safe. And if you look at the voltage is about 2.2 per unit at a 380 kV system. We are looking at the SIL of 1300, which is way below the SIL of the equipment. So that means for this scenario, there is no violation. Now I'm going to conclude my presentation. We're going to pause for a few minutes to look at some of your questions and try to answer them. So the first question is there a document which describes the steps of statistical breaker study? We are working on making a more comprehensive document for statistical breaker. At the moment, the only document available is help component in master library. The next question is, where can I find the result of a statistical breaker, like a maximum, minimum? Well, I can show you that one right now. I think the other case we were running is still running, but I can pause this one and show you how to get the result. So when you run a case, it will generate a folder. Depends on the compiler you're using. It's either GF42 or Intel Fortran 12 or a higher version. If you go inside that folder, there's a output file recorded. See, these are the two multiple run output files. So if you open them, so these are all the voltages recorded for each run. And at the end, you can see for each variable, there's a minimum, maximum, mean value, standard deviation, 2% level, and 98% level. And remember, the 2% level is mean minus 2.054 times standard deviation. And the maximum, the 98% level is mean plus 2.054 times standard deviation. So this will be mean minus 2.054 times standard deviation. And similarly for the 98% is mean plus 2.054 times STE. The next question was, how about saturation of shunt reactor? Should they be modeled as saturable reactors? If you do have a data for them, you can represent them as a saturable reactor. If not, you can model them as a simple reactor. The next question is, are transpositions model available in the library? As I show you in my, I can quickly go back to the presentation. By transposition model, if you mean the wires, the way they're connected here, yes, they are available in master library. The next question is, do you use the high frequency model of the surge arrestor? It does not require for switching study. If you're doing a higher frequency type transient studies, like a very fast transient or lightning, then you may want to consider that. The next question is, what is your time step of simulation? We are looking at a kilohertz range. So if you are having ten microsecond should be sufficient enough for the switching study. Because if you look at the table here, so for the switching, we're looking at 20 microsecond to 5,000 microsecond for the slow front. So if your simulation time step is 10 microsecond, it should provide you with enough sample. It also depends on the length of the line or cables you have in your model too. So if you have a really short lines and cable in the network, then you may need to adjust your time step accordingly. The next question is, what should be the status of neighboring generators during SOV or TOV study? They should be in their steady state operation. So whatever value you get from load flow, you should achieve that value before you apply your switching study. This is the time I have to answer all the questions. I'm sure there are more questions coming in. Please send those questions to our PSCAD support. We try to answer them the best we can. Thank you very much. Have a good one.